Another common form of potential energy is spring potential energy. Now, springs were introduced a bit in chapter 5 at the end, talking about elasticity, but we skipped over that part. We're going to reintroduce that section of chapter 5 when we talk about chapter 9, equilibrium and elasticities. But we do need to talk about springs before we get to that point. So, when you compress or stretch a spring, think of like a coil of metal, like the springs on old cars, suspension. When you compress that or stretch a spring, like a slinky, the spring exhibits a force attempting to restore the equilibrium position. This is called a restoring force. So in my example here, imagine we have a wall. Attached to that wall is a stiff spring that's attached to a mass sitting on a frictionless surface. So, if you grab that mass and pull it away from the wall or push it away from the wall, you stretch the spring. The spring has to stretch out as that mass gets further from the wall. That spring then will exhibit a force pulling it back to the wall. It's a restoring force. It's trying to get that mass back to the position x equals 0. If you pull a spring some distance x from its equilibrium position, and the equilibrium position here is just the rest position the spring wants to sit at. If you pull it some distance x from its equilibrium position, you will get a force. Now it's a spring, so the more you stretch it, the stronger that force gets. I don't know if any of you have ever used like one of those rubber band-based exercise pieces of equipment. But those large rubber bands, you can stretch it a little bit easily, but it takes more effort to pull it further. Or an old school bow and arrow, not the old classical bow and arrow. Stretching a bow and arrow a little bit is easy. Pulling it a long distance takes a lot more force. So this is not a constant force problem. It's also a restoring force, which means that the force is always in the opposite direction of the displacement. Here my displacement is in the positive direction. I'm stretching this spring. The force then is in the negative direction. If I, instead of stretching the spring, I push this mass and try to compress the spring again pushes back in the opposite direction. So there's a famous law called Hooke's law. Hooke's law basically states that the force on a spring is in the opposite direction of its displacement, so that's why there's a negative sign here. Its displacement x is measured from the equilibrium position, and k, lowercase k here, is what's called a spring constant. Now, not to be confused with kinetic energy, which is also sometimes represented by k. I think your book uses ke. For kinetic energy. This lowercase k is a spring constant. You can think of it as a stiffness to the spring, right? This k tells you what the force will be given a certain displacement x. So for weak springs, it's easy to stretch them and compress them. There's not much of a force that you get back from those weak springs. A very, very stiff spring, imagine like, car suspension or truck suspension, those springs are very stiff. They have a very large spring constant, so it requires a great deal of force to have a small amount of compression or expansion. So these are springs. Now, because there are forces involved and you're moving this object through some displacement, work is being done when you displace a spring. When you compress or stretch a spring, work is being done. Where does that work go, right? Work is a transfer of energy. Where does the energy go? Well, the energy can be stored in the spring. If you imagine those old school dart guns, where you push a dart down the barrel, the dart compresses a spring. That's compressed spring stores energy, which is released when you pull the trigger of the dart gun and the dart flies out. Or the old school watches. We used to have torsion springs, basically. So you would wind the old school watch up, and you would wind up a spring, and as that spring slowly unwound, it would drive the watch mechanism. Just like an old grandfather clock had weights where you draw up the weights and use gravitational potential energy of the weights. As they slowly descended, they powered the clock. Old school pocket watches use springs. So you can store energy in the compression or the stretching of a spring. And how much energy is stored, we'll talk about in just a bit. All right, now we're talking about spring potential energy. Spring potential energy, or PE with a subscript of S standing for spring, is equal to 1/2 times lowercase k, which is the spring constant we just mentioned before from Hooke's law. This k depends on the spring. That's not something that you can just look up in a table and say, oh, iron has a spring constant of blah. That's not how it works. It depends on how the spring is manufactured, how thick the spring is, how stiff the spring is. This is something you can determine experimentally, or maybe a manufacturer will tell you what their target spring constant is. And x squared, where x again is the displacement from the equilibrium position. So, unlike previously when we talked about x as just being a position, this spring displacement assumes x equals 0 is at the equilibrium position. So x here represents how far did you move it from the equilibrium. Notice that motion doesn't, I don't care if it's positive or negative. If it's negative, you're squaring it, so it'll be positive anyway. So 1 centimeter displacement in compression versus a 1 centimeter displacement in expansion, the same results occur. Now there is one caveat, and we'll get to it in more detail in chapter 9. They do talk about it in chapter 5 a little bit, is that springs, the force Hooke's law and the potential energy equations only work over a limited range of displacements, right? Some of you might have, as children, had the old metal slinkies, and you pull them out too far, and then they don't go back together quite the same. You can have elastic limits. Things will stretch only so far before they don't work the same anymore. Think of a rubber band. You can stretch a rubber band, but eventually you stretch a rubber band so much that it snaps. So here's the equation for spring potential energy. Compare that to gravitational potential energy, which is the mass of the object times the acceleration due to Earth's gravity times the height that object is at. And again, height is measured from some unlike displacement here, which is measured from the equilibrium position, this height is measured from some arbitrary position. I usually, in any of my problems that I solve, I have the height as 0 at the lowest point. So the ground or the roller coaster goes down to some height 10 meters. You know, you can either put that as your height 0 or the ground is height 0. Because for gravitational potential energy, you're typically looking at the potential differences between two heights. And then kinetic energy, 1/2 mv squared. Again, v is the speed of the object, m is the mass of the object. These are all scalars. They're all energies. They're all measured in joules. Together, these three things make up mechanical energy, as opposed to chemical energy, where energy is stored between the bonds of atoms, or nuclear energy, where energy is stored within the nucleus, the bonds between the protons and neutrons in the nucleus itself. These are physical, real-world, macroscopic types of energy. Together, these three things form mechanical energy. And conservation law states that mechanical energy is conserved in the presence of conservative forces. Spring forces are conservative. Right? If you've ever taken a spring and displaced it and let it go, it wobbles back and forth. It's constantly changing kinetic energy into spring potential energy and back. Or a roller coaster cart going over the waves. It should, without friction, should go on forever. These are mechanical energy. And if gravity is a conservative force, spring force is a conservative force. So as long as there's no friction or drag, these three energies in a system must always have the same total. They don't have to be the same. All the energy could be in kinetic, or all the energy could be in the spring, or all the energy could be in gravitational potential. But they have to add up to the same amount. So in a simple example, let's imagine you have a compressed spring with some box of mass m on it. and it's attached by some kind of a latch, and you can fire it. Well, what happens if you fire that spring? Well, the box will move upwards, right? The energy stored in the spring goes into changing the gravitational potential energy, the box goes up, and the kinetic energy, the box gets faster. Once the box leaves the spring, and is no longer attached to that platform, all the spring energy went into that box. That box is now ascending, but slowing. And eventually it'll reach some maximum height where the spring potential energy is zero because the spring is sprung, spent. The kinetic energy is zero because at the top of the height, the box goes up to a certain height, stops, and then starts to descend. So the speed at the height of that moment is zero. And the gravitational potential energy will be at a maximum. So if you know how much energy is stored in the spring, you can actually figure out how high the box goes because these total energies have to be the same. Right? Initially, gravitational potential energy, I'll define this height to be zero. So the object at that moment has no gravitational potential energy. It's not moving, so it has no kinetic energy. All of the energy is in the spring. After I fire it and the box moves up to its highest point, at its highest point, there's no energy stored in the spring anymore. There's no kinetic energy because at its highest point, its speed is zero for that instant. Therefore, all of the energy that was in the spring is now in gravitational potential energy, and I can figure out how high the box went from that calculation. Again, assuming no frictional forces, no drag forces. So this is conservation of mechanical energy. Now, if you do have frictional or drag forces, you can still look at these conservation laws, but some of the energy will be sapped from the system. In the analogy I used before, I talked about how kinetic energy was like your checking account and gravitational potential energy was like your savings account, and that every time you could move money from one to the other, but your total amount of money or the total amount of energy in the system always stayed the same. Well, here with spring potential energy, we just added a third savings account. So now your money can either be in your checking, your first savings, or your second savings. But still, as long as you're moving money just between savings accounts or between savings and checking, the total amount of money you have doesn't change. Those are conservative forces, conservation of mechanical energy. Non-conservative forces would be as if you had a transaction fee every time you moved money. Let's imagine every time you moved money from one account into another account, your bank charged you $1. Well, now every time you change energy, you lose money, right? You lose energy. Some of that energy is sapped out. In the bank analogy, some of your money disappears because of transaction fees. And eventually, do enough transactions, all your money is gone. Do enough motion, here, all your money is gone. So for the example we have here of the spring, imagine this box bouncing up and down on this platform like a trampoline. Eventually, in real life, there are frictional forces. There's drag resistance. The box will bounce up, get less high, less high, less high, and then eventually stop. So all of the energy that was in the spring, all of the energy that was in the motion of the box, all of the energy that was in the gravitational potential energy is now gone. It's gone into thermal energy elsewhere. So many times that gravitational potential energy, spring potential energy, and kinetic energy changed hands, the transaction fees sapped all the energy out. Again, using my bank analogy. So let's look a bit more at non-conservative forces and their effects on conservation of energy in the next video.